Okay, in this lecture, the diversity of matter, we're going to put together two concepts, polar bonds and polar molecules. So we're going to be using our polar bonds concept, bond polarity, based on differences in electronegativity, and we're going to combine that with our VSEPR theory to come up with an idea about what polar molecules are and if a molecule is polar or isn't polar based on its shape. So pages 57 to 62 in your textbook. And by the end of this lecture, you'll be able to predict the polarity of a molecule based on the bond polarity and the molecule's three-dimensional shape. And we'll also briefly describe the shape and bonding in something called a network solid. So bond polarity, just to review, is caused by differences in electronegativity between atoms that are sharing electrons. It results in an electrostatic charge difference between the atoms on either end of the bond. So one end of that bond is going to have an atom that's positively charged, and one end of that bond is going to have an atom that is negatively charged. So molecules can be polar if it has polar bonds, and if those polar bonds aren't pulling against each other. And I'll show you what I mean. So we need to know the stereochemistry of the molecule and its bond dipoles. And here's an example. Here we have two polar molecules. This is water and carbon dioxide. Now if we take a look at water, this is a polar molecule. There's a big difference in electronegativity between hydrogen and oxygen. Hydrogen has an electronegativity of 2.2. Oxygen has an electronegativity of 3.4. So we have a 1.2 difference in electronegativity. So each of these bonds, the bond between hydrogen and oxygen, it's polar, and its dipole goes towards oxygen. Oxygen is pulling on electrons. And the same thing's happening here. So here's our two bond dipoles. When we add them together, so when we take those two bond dipoles, so here's force 1 from that first arrow that we drew, and then force 2. When we add force 2 to it, and I'll just draw it up here, tip to tail, we end up with a resulting force on the atom. So we end up with what's called a polar molecule that has a slightly negative end at one side and a slightly positive end at the other side. So this molecule has polar bonds, and it's a polar molecule. When we look at carbon dioxide, notice that carbon dioxide has polar bonds as well. Again, oxygen has a 3.4 electronegativity. Carbon has 2.4. Sorry, 2.6. So it's a difference of 0.8. And so it's not as polar as those hydrogen and oxygen bonds, but it's still polar. It's still polar bonds. But if we take a look, the polarity of one bond is pulling in this direction. That oxygen is pulling on the electrons harder than carbon, and the other one is pulling in this direction. The other oxygen is also pulling on electrons. So what we have is a tug of war, and both forces are the same. There's a 0.8 force pulling in one direction, a 0.8 force pulling in the other direction, so our net pull is 0. So here we have a molecule with polar bonds, but it is a nonpolar molecule. So just because there are polar bonds, it does not ensure that the molecule is also polar. So in order to determine molecular polarity, we draw the Lewis diagram of the molecule, we get the VSEPR rules out, and we draw the shape diagram, and then we use electronegativities to determine if there are bond dipoles. Once we know that, we add up our vectors, and if our bond dipoles don't cancel out, then we end up with a polar molecule. If our vectors do cancel out, like they did for carbon dioxide, we get a non-polar molecule. And so if you take a look, there's also a table on page 59 in your inquiry into chemistry that helps you determine if the molecule is polar or not polar. So we're just going to go through a bunch of examples. just to see when we end up with polar molecules and non-polar molecules. So I have, for NH3, we've drawn this a few times now, so I'm just going to skip ahead a little bit. We know that NH3 is a nitrogen center with 3 hydrogens. Its Vesper class is AX3E, and so we know this is going to be a trigonal pyramidal molecule in terms of its shape diagram. We would have something that looks like this: one wedge, one dotted line, and one hydrogen in the same plane as our nitrogen. And our bonds are polar. So since we have, these are all nitrogen-hydrogen bonds, and these are all actually very polar, if you find their differences in electronegativities, which means this nitrogen is pulling on the electrons of all of these hydrogens. Now, since our vectors are all pulling in the same direction, when they add up, they're going to add up in such a way that the molecule will be polar. So because they don't cancel out, it's going to be a polar molecule. It has polar bonds. The bonds aren't opposite each other, so it's going to be a polar molecule. For N2, it's going to be 2 nitrogens. They have a triple bond between them. In terms of our Vesper class, we can choose either center. I'll choose this one. It's a AX E molecule. And what this really means is we have one lone pair, we have one or 3 sets of bonding electrons, and so this is going to be, there's only 2 atoms in this molecule, so it's going to be linear, and the difference in electronegativity between 2 atoms are the same, is 0, so they are non-polar bonds. So it's going to be a non-polar molecule. Try some more. The Lewis diagram for HBr. Bromine has its 8 valence electron, hydrogen has 2. Its Vesper class is AXE3. We'll use bromine as our center just to make it easier. And we end up with a linear molecule again. Our shape diagram is pretty easy. And the difference in electronegativity is large. You can find them using your periodic table, but it is large. It's a polar bond where bromine is pulling on the electrons. And since it's the only vector there, there's nothing to cancel it out, so it's a polar bond. And it's a polar molecule. Alright, CH3I. We're going to have carbon. It has 1 hydrogen and 3 iodines. Each of the iodines has 8 valence electrons. And so it is an AX4 molecule. It has no lone pair, so it's going to be tetrahedral. And its shape diagram is going to be something like this. See, 1 iodine in the plane, 1 iodine, oops, coming towards us, and one iodine going away from us. Now when we draw the vector diagram, well, first we'll find bond polarity. So we have two different types of bonds, so we're going to write down the differences in electronegativity. The difference in electronegativity between carbon and hydrogen is small. It's 0.4, so it's not a very polar bond. The differences in electronegativity between carbon and iodine is even smaller. It's 0.1. So, and these are going to be pulling away. So if we draw this bond polarity, what we'd see, where's my little marker here, is there's a polarity pulling towards the carbon, and then very slight polarities, almost non-polarities really, pulling out towards the iodines. So what this means is this molecule is nonpolar. The bonds are not very polar, and for the most part they cancel each other out. There might be, it's going to be nonpolar to slightly polar. Because these two vectors here would add this one here pulling down, and this one here pulling, well, there'd be some force pulling down as well this way. So they would add up a little bit, but again, because they're not very polar bonds to begin with, both of them are only slightly polar, the molecule might be slightly polar. Alright, C2, H3. Alright, this is a molecule that's going to have two centers with 3 hydrogens, 2 on each carbon, one there, one there, one there, and then chlorine we'll put in our bond. And this is actually going to be a molecule with a double bond in the center in order to satisfy those carbons. And this chlorine has a full valence shell. So our carbons each have 8 electrons. Our hydrogens all have 2. They're happy. So there's our Lewis diagram. In terms of Vesper class, now we have 2 centers. So we'll look at each center separately. This carbon here is an AX3 molecule. No lone pairs. The other carbon is also an AX3 molecule. So both of these are going to be trigonal planar. And the easiest way to draw this one is to line your carbons up horizontally and then put out your hydrogens and your chlorine. And then you have your one triangle around one carbon and another triangle around your other carbon. And there's your 2 trigonal planar shapes. So I'm just going to clear this up. I wanted to show you the 2 trigonal planar shapes. Now I'm going to clear it off here, and we're going to redraw our shape diagram just so I can draw those bond dipoles. All right. So we have 2 carbons, hydrogens, chlorine, hydrogen. Now, if we take a look, the carbon-carbon bond isn't going to be polar because the difference is 0. So our difference in electronegativity for a carbon-carbon bond is 0. The difference in electronegativity for a carbon-hydrogen bond is 0.4, so it's slightly polar. The only other bond we have is a carbon-chlorine bond. That one's a little bit more significant. Chlorine has an electronegativity of 3.2, carbon's 2.6, so that's a difference in electronegativity of 0.6. So this is actually, it's a polar bond. And it's pulling, the electrons are being pulled towards the chlorine. Since it's really the only polar bond, there's nothing to cancel it out. The only bond that could cancel it out would be this one, and its polarity is smaller. So because it's smaller, this molecule is going to be polar. It's not going to be very polar, but it'll be polar. When we compare it to the molecule underneath it, it has the same Lewis structure minus the chlorine. So it's also going to be AX3, AX3. So our centers are going to be trigonal planar. The difference is this molecule is going to be nonpolar. The bonds are slightly polar, but because they cancel out, this polarity would cancel with this polarity, and this polarity would cancel with this polarity. So because all of our polarities are pulling against each other, we definitely end up with a nonpolar molecule. All right, let's keep on trucking. For OCl, the Lewis diagram would be something like that. The Vesper class is a X2, E2. Remember, they were just looking at our central atom here. And so this molecule is going to be bent. And it's bent based on a tetrahedron. So the shape diagram would be something like this. Our bonds, the difference in electronegativity is 0.2 for each of our bonds, and it's pulling towards the oxygen. So we have a polarity pulling this way, a polarity pulling this way. When we add them together, since they're pulling in different directions, or I should say since they're not pulling in opposite directions, they won't cancel each other out. So this molecule is going to be slightly polar because the bond dipoles are not canceling each other out. SiCl4 is going to have a silicon center and chlorines around the outside, and each of those chlorines is going to have its 8 valence electrons. Its Vesper class is going to be AX4. We're just looking at the silicon here. It has 4 atoms around it, so it's going to be a tetrahedron. And because all the bonds are the same in terms of their electronegativity, it doesn't even matter if the bonds are polar or not. It's going to be a nonpolar molecule. So all of these bonds are pulling at 4 vertices of a tetrahedron. So even though they are very polar bonds, silicon only has an electronegativity of 1.9. Chlorines have an electronegativity of 3.2. So it's going to be a difference in electronegativity of 1.3. So all of these bonds, all of the polarities are pulling out towards the chlorines, but because they're all on corners of a tetrahedron, they're all going to cancel, and so we're going to end up with a nonpolar molecule. All right. Here we have carbon. It's going to be bonded to the oxygen and 3 of the hydrogens. That oxygen in turn is going to be bonded to the last hydrogen. And so this molecule has 2 centers. The carbon center is an AX4, so it's going to be tetrahedral. I'll just do this to save myself some space. And the oxygen is a X2, E2. It has 2 lone pairs, so it's going to be bent. And so when we draw our shape diagram, what I'm going to do is I'm going to put that carbon and oxygen in the same plane. I'll bend the hydrogen out. I'll put this hydrogen in the same plane as well. And then what we have is one hydrogen moving away, one hydrogen moving towards. And when we take a look at our bond polarities, we have carbon-hydrogen bonds, we have a carbon-oxygen bond, and we have an oxygen-hydrogen bond. And remember, oxygen and hydrogen, they have a fairly difference in electronegativity. This is a large difference in electronegativity. Carbon and oxygen has a fairly large difference in electronegativity. And they're both pulling towards the oxygen. So we have a vector pulling in this direction and a vector pulling in this direction. The carbon-hydrogen bonds are slightly polar, but nothing compared to these two. When you add these two together, since they aren't pulling in opposite directions, we're going to have a polar molecule. And ozone has a shape or a Lewis diagram similar to this. It's actually a resonance structure, but for Vesper class, our central atom is a X2 with 1 lone pair, so it's going to be bent, but based on trigonal planar. And since the difference in electronegativity for all of our bonds is 0, it's going to be a nonpolar molecule. So one more topic to cover here. We have network solids. Network solids are special types of substances joined together by covalent bonds. They can be gathered up into groups of dozens up to millions, and in terms of structure, they're similar in structure to ionic compounds in terms of forming that crystal lattice, but instead of the particles being held together by static charge of ionic bonds, they're held together by sharing electrons and covalent bonds. The examples that you need to know are carbon and silicon. If we have pure carbon or pure silicon, so for example just pure silicon, carbon and silicon are special because they have 4 bonding electrons. And so what happens is your carbons can bond forever in a variety of patterns. And so what you end up having is carbon always bonding to other carbons. You can even end up in these cases where you have carbons bonded up in groups and pairs, and sometimes they'll form double and triple bonds. So carbon and silicon has the same property. it can bond to itself forever because it always has so many bonding electrons free. Silicon dioxide, which is quartz, same property. Usually what ends up happening is you end up with a silicon and it starts binding to a variety of oxygens. And so each silicon binds to 4 oxygens, and each of these oxygens is able to bond to silicon, and you end up again with this large structure that goes on forever. So in terms of the carbon network solids, carbon can actually form a variety of what are called allotropes. Allotropes are different versions of elemental carbon based on the types of bonds between them. And we all know that carbon atoms can form things like graphite, like pencil lead. And so what happens is pencil lead actually has carbon bonding that looks like this. It bonds in sheets, and then those sheets are slightly attracted to each other, making the substance kind of slippery, and that's what gets the graphite or the pencil lead out of your pencil. Another form that we're all sort of familiar with is diamond. And diamond, I believe, is this one. And it forms a very rigid, hard, almost indestructible structure, one of the hardest minerals on Earth. Carbon is also used in technology to form things like nanotubes. These are very, very, very tiny tubes that can then be used for nanotechnology in terms of circuitry or even in medicine. So a whole bunch of neat shapes all formed by just the carbon atom. So for homework, there's some more practice problems, 11 to 16 to get you to practice your bond polarity. And for your network solids, if you just remember that carbon can form network solids and silicon can form network solids, that's pretty much what you need to know.